a real number or a natural number.
Yeah, every object sort of comes with a history of where it came from, and you can kind of trace it.
Oh, I see.
So it's designed for reliability. So modern AIs are not used it's a disjoint technology. People are beginning to use AIs on top of Lean. So when a mathematician tries to program a proof in Lean, often there's a step, okay, now I want to use the fundamental theorem of calculus, say, okay, to do the next step. So the Lean developers have built this massive project called MathLib, a collection of tens of thousands of useful facts about mathematical objects. And somewhere in there is the fundamental theorem of calculus, but you need to find it. So a lot of the bottleneck now is actually lemma search. There's a tool that is in there somewhere, and you need to find it. And so there are various search engines specialized for MathLib that you can do. But there's now these large language models that you can say, I need the fundamental theorem of calculus at this point. And it's like, okay, for example, when I code, I have GitHub Copilot installed as a plugin to my IDE. And it scans my text and it sees what I need. It says, I might even type here, okay, now I need to use the fundamental theorem of calculus, okay? And then it might suggest, okay, try this. And like maybe 25% of the time, it works exactly. And then another 10, 50% of the time, it doesn't quite work, but it's close enough that I can say, oh yeah, if I just change it here and here, it'll work. And then like half the time, it gives me complete rubbish. But people are beginning to use AIs a little bit on top. Mostly on the level of basically fancy autocomplete, that you can type half of one line of a proof and it will tell you.
Yeah, but a fancy, especially fancy with the sort of capital letter F, is remove some of the friction a mathematician might feel when they move from pen and paper to formalizing.
Yes, yeah. So right now I estimate that the time and effort taken to formalize a proof is about 10 times the amount taken to write it out. Yeah, so it's doable, but it's annoying.
But doesn't it like kill the whole vibe of being a mathematician?
Yeah.
Just
so I mean,
having a pedantic coworker.
Right. Yeah. If that was the only aspect of it, okay. But okay, there's some cases where it's actually more pleasant to do things formally. So there's a theorem I formalized, and there was a certain constant 12 that came out of in the final statement, and so this 12 had to be carried all through the proof, and like everything had to be checked that it goes all these other numbers that had to be consistent with this final number 12. And then so we wrote a paper through this theorem with this number 12, and then a few weeks later, someone said, "Oh, we can actually improve this 12 to an 11 by reworking some of these steps." And when this happens with pen and paper, like every time you change your parameter, you have to check line by line that every single line of your proof still works. And there can be subtle things that you didn't quite realize. Some properties of number 12 that you didn't even realize that you were taking advantage of. So a proof can break down at a subtle place. So we had formalized the proof with this constant 12. And then when this new paper came out, we said, oh, okay, so that took like 3 weeks to formalize and like 20 people to formalize this original proof. I said, oh, but now let's update the 12 to 11. And what you can do with Lean is that you just, in your headline theorem, you change it 12 to 11, you run the compiler, and like of the thousands of lines of code you have, 90% of them still work, and there's a couple that are lined in red. Now I can't justify these steps, but it immediately isolates which steps you need to change, but you can skip over everything which works just fine. And if you program things correctly, with sort of good programming practices, most of your lines will not be red. And there'll just be a few places where if you don't hard code your constants, but you sort of, you use smart tactics and so forth, you can localize the things you need to change to a very small period of time. So it's like within a day or two, we had updated our proof. Because this is a very quick process. You make a change. There are 10 things now that don't work. For each one, you make a change, and now there's 5 more things that don't work. But the process converges much more smoothly than with pen and paper.
So that's for writing. Are you able to read it? Like if somebody else sends a proof, are you able to what's the versus paper and?
Yeah, so the proofs are longer, but each individual piece is easier to read. So if you take a math paper and you jump to page 27 and you look at paragraph 6 and you have a line of text of math, I often can't read it immediately, because it assumes various definitions, which I have to go back and maybe on 10 pages earlier this was defined. And this the proof is scattered all over the place, and you basically are forced to read fairly sequentially. It's not like, say, a novel where, like, in theory you could open up a novel halfway through and start reading. There's a lot of context. But when a proof in Lean, if you put your cursor on a line of code, every single object there, you can hover over it, and it would say what it is, where it came from, where stuff is justified. You can trace things back much easier than sort of flipping through a math paper. So one thing that Lean really enables is actually collaborating on proofs at a really atomic scale that you really couldn't do in the past. So traditionally, pen and paper, when you want to collaborate with another mathematician, either you do it at a blackboard where you can really interact, but if you're doing it sort of by email or something, basically, you have to segment it. So I'm gonna finish section 3, you do section 4, but you can't really sort of work on the same thing collaboratively at the same time. But with Lean, you can be trying to formalize some portion of the proof and say, I got stuck at line 67 here. I need to prove this thing, but it doesn't quite work. Here's the 3 lines of code I'm having trouble with. But because all the context is there, someone else can say, oh, okay, I recognize what you need to do. You need to apply this trick or this tool. And you can do extremely atomic level conversations. So because of Lean, I can collaborate, with dozens of people across the world, most of whom I have never met in person. And I may not know actually even whether they're, how reliable they are in their, in the proof they give me, but Lean gives me a certificate of trust. So I can do trustless mathematics.
So there's so many interesting questions. So one, you're known for being a great collaborator. So what is the right way to approach solving a difficult problem in mathematics when you're collaborating? Are you doing a divide and conquer type of thing, or are you focusing on a particular part and you're brainstorming?
There's always a brainstorming process first. Yeah, so math research projects, sort of by their nature, when you start, you don't really know how to do the problem. It's not like an engineering project where somehow the theory has been established for decades and its implementation is the main difficulty. You have to figure out even what is the right path. So this is what I said about cheating first. It's like to go back to the bridge building analogy. So first assume you have an infinite budget and like unlimited amounts of workforce and so forth. Now can you build this bridge? Okay. Now have infinite budget but only finite workforce. Right? Now can you do that and so forth? I mean, of course, no engineer can actually do this because they have fixed requirements. Yes, there's this sort of jam sessions always at the beginning where you try all kinds of crazy things and you make all these assumptions that are unrealistic, but you plan to fix later. And you try to see if there's even some skeleton of an approach that might work. And then hopefully that breaks up the problem into smaller sub-problems, which you don't know how to do, but then you focus on the sub-ones. And sometimes different collaborators are better at working on certain things. So one of my theorems I'm known for is a theorem of Ben Green, which is now called the Green-Tao theorem. It's a statement that the primes contain arithmetic progressions of any length. So it was a modification of this theorem of Semiretti. And the way we collaborated was that Ben had already proven a similar result for progressions of length 3. He showed that sets like the primes contain lots and lots of progressions of length 3, even subsets of the primes, certain subsets do. But his techniques only worked for length 3 progressions. They didn't work for longer progressions. But I had these techniques coming from ergodic theory, which is something that I had been playing with and I knew better than Ben at the time. And so if I could justify certain randomness properties of some set relating to the primes, like there's a certain technical condition which, if I could have it, if Ben could supply me this fact, I could conclude the theorem. But what I asked was a really difficult question in number theory, which he said, no, there's no way we can prove this. So he said, can you prove your part of the theorem using a weaker hypothesis that I have a chance of proving it? And he proposed something which he could prove, but it was too weak for me. I can't use this. So there was this conversation going back and forth. It's sort of a
different cheats too.
Yeah. I want to cheat more, he wants to cheat less. Okay.
Yeah.
But eventually we found a property which A, he could prove, and B, I could use. And then we could prove our theorem. So there are all kinds of dynamics, I mean, it's every collaboration has some story. No two are the same.
And then on the flip side of that, like you mentioned with lean programming, now that's almost like a different story because you can create, I think you've mentioned a kind of a blueprint
right
for a problem, and then you can really do a divide and conquer with lean, where you're working on separate parts,
right,
and they're using the computer system proof checker essentially, to make sure that everything is correct along the way.
So it makes everything compatible and and trustable. So currently only a few mathematical projects can be cut up in this way. At the current state of the art, most of the lean activity is on formalizing proofs that have already been proven by humans. A math paper basically is a blueprint in a sense. It is taking a difficult statement like big theorem and breaking up into maybe 100 little lemmas, but often not all written with enough detail that each one can be sort of directly formalized. A blueprint is like a really pedantically written version of a paper where every step is explained as much detail as possible, and to try to make each step kind of self-contained, or depending on only a very specific number of previous statements that have been proven, so that each node of this blueprint graph that gets generated can be tackled independently of the others, and you don't even need to know how the whole thing works. So it's like a modern supply chain. Like if you want to create an iPhone or some other complicated object, no one person can build up a single object, but you can have specialists who just, if they're given some widgets from some other company, they can combine them together to form a slightly bigger widget.
I think that's a really exciting possibility because you can have, if you can find problems that could be broken down this way, then you can have, thousands of contributors, right?
Yes,
it could be completely distributed.
Yeah. So I told you before about the split between theoretical and experimental mathematics. And right now, most mathematics is theoretical and only a tiny bit is experimental. I think the platform that Lean and other software tools, GitHub and things like that, they will allow experimental mathematics to scale up to a much greater degree than we can do now. So right now, if you want to do any mathematical exploration of some mathematical pattern or something, you need some code to write out the pattern. And I mean, sometimes there are some computer algebra packages that can help, but often it's just one mathematician coding lots and lots of Python or whatever. And because coding is such an error-prone activity, it's not practical to allow other people to collaborate with you on writing modules for your code, because if one of the modules has a bug in it, the whole thing is unreliable. So you get these bespoke spaghetti code written by not professional programmers, but by mathematicians, and they're clunky and slow, and so because of that, it's hard to really mass produce experimental results. But I think with Lean, I mean, so I'm already starting some projects where we are not just experimenting with data, but experimenting with proofs. So I have this project called the Equational Theories Project. Basically, we generated about 22 million little problems in abstract algebra. Maybe I should back up and tell you what the project is. Okay, so abstract algebra studies operations like multiplication and addition and their abstract properties. Okay, so multiplication, for example, is commutative. X times y is always y times x, at least for numbers. And it's also associative. X times y times z is the same as x times y times z. These operations obey some laws that don't obey others. For example, x times x is not always equal to x. So that law is not always true. So given any operation, it obeys some laws and not others. And so we generated about 4,000 of these possible laws of algebra that certain operations can satisfy. And our question is, which laws imply which other ones? So for example, does commutativity imply associativity? And the answer is no, because it turns out you can describe an operation which obeys the commutative law but doesn't obey the associative law. So by producing an example, you can show that commutativity does not imply associativity. But some other laws do imply other laws by substitution and so forth. And you can write down some algebraic proof. So we looked at all the pairs between these 4,000 laws, and there's about 22 million of these pairs. And for each pair, we ask, does this law imply this law? If so, give a proof. If not, give a counterexample. So 22 million problems, each one of which you could give to an undergraduate algebra student, and they had a decent chance of solving the problem. Although there are a few, at least 22 million, there are like 100 or so that are really quite hard. Okay, but a lot are easy. And the project was just to work out, to determine the entire graph, like which ones imply which other ones.
That's an incredible project, by the way. Such a good idea, such a good test of the very thing we've been talking about at a scale that's remarkable.
Yeah, so it would not have been feasible. I mean, the state of the art in the literature was 15 equations and sort of how they imply. That's sort of at the limit of what a human with pen and paper can do. So you need to scale it up. So you need to crowdsource, but you also need to trust all the. No one person can check 22 million of these proofs. Okay? You need it to be computerized, and so it only became possible with Lean. We were hoping to use a lot of AI as well. So the project is almost complete. So of these 20 million, all but 2 had been settled.
Wow.
And and of those 2, we have a pen and paper proof of the 2, and we're formalizing it. In fact, this morning I was working on finishing it. So we're almost done on this.
It's incredible.
It's fantastic.
How many people were able to get?
About 50. Which in mathematics is considered a huge number.
It's a huge number. That's crazy.
Yeah. So we're going to have a paper with 50 authors and a big appendix of who contributed what.
Here's an interesting question, not to maybe speak even more generally about it. When you have this pool of people, is there a way to organize the contributions by level of expertise of the people, of the contributors? Now, okay, I'm asking a lot of pothead questions here, but I'm imagining a bunch of humans and maybe in the future some AIs.
Yeah.
Can there be like an ELO rating type of situation where like a gamification of this?
The beauty of these Lean projects is that automatically you get all this data. Yeah. So like everything's to be uploaded to this GitHub, and GitHub tracks who contributed what. So you could generate statistics from at any later point in time. You can say, oh, this person contributed this many lines of code or whatever. I mean, these are very crude metrics. I would definitely not want this to become part of your tenure review or something. But I mean, I think already in enterprise computing, right, people do use some of these metrics as part of the assessment of performance of an employee. Again, this is a direction which is a bit scary for academics to go down. We don't like metrics so much.
And yet academics use metrics. They just use old ones. Number of papers.
Yeah, it's true. It's true that, I mean...
it feels like this is a metric, while flawed, is going more in the right direction, right?
Yeah.
It's an interesting, I mean, at least it's a very interesting metric.
Yeah, I think it's interesting to study. I mean, I think you can do studies of whether these are better predictors. There's this problem called Goodhart's law. If a statistic is actually used to incentivize performance, it becomes gamed, and then it is no longer a useful measure.
Oh, humans always.
Yeah, no. I mean, it's rational. So what we've done for this project is self-report. So there are actually these standard categories from the sciences of what types of contributions people give. So there's concept and validation and resources and coding and so forth. So we there's a standard list of 12 or so categories. And we just ask each contributor there's a big matrix of all the authors in all the categories, just to tick the boxes where they think that they contributed. And just give a rough idea, so you did some coding and you provided some compute, but you didn't do any of the pen and paper verification or whatever. And I think that works out. Traditionally, mathematicians just order alphabetically by surname. So we don't have this tradition as in the sciences of, lead author and second author and so forth, which we're proud of. We make all the authors equal status, but it doesn't quite scale to this size. So a decade ago, I was involved in these things called polymath projects. it was a crowdsourcing mathematics, but without the lean component. So it was limited by, you needed a human moderator to actually check that all the contributions coming in were actually valid. And this was a huge bottleneck, actually. But still, we had projects that were, 10 authors or so. But we had decided at the time not to try to decide who did what, but to have a single pseudonym. So we created this fictional character called DHJ Polymath. In the spirit of Bourbaki, Bourbaki is the pseudonym for a famous group of mathematicians in the 20th century. But and so the paper was authored under pseudonym, so none of us got the author credit. This actually turned out to be not so great for a couple of reasons. So one is that if you actually wanted to be considered for tenure or whatever, you could not use this paper in your as you submitted as one of your publications, because it didn't have the formal author credit. But the other thing that we've recognized much later is that when people referred to these projects, they naturally referred to the most famous person who was involved in the project. Oh, so this was Tim Gower's Polymath project. This was Terence Tao's Polymath project, and not mention the other 19 or whatever people that were involved.
Yeah.
So we're trying something different this time around, where we have everyone's an author, but we will have an appendix to this matrix, and we'll see how that works.
I mean, so both projects are incredible. Just the fact that you're involved in such huge collaborations. But I think I saw a talk from Kevin Buzzard about the lean programming language just a few years ago, and he was saying that this might be the future of mathematics. And so it's also exciting that you're embracing one of the greatest mathematicians in the world, embracing this, what seems like the paving of the future of mathematics. So I have to ask you here about the integration of AI into this whole process. So DeepMind's alpha proof was trained using reinforcement learning on both failed and successful formal lean proofs of IMO problems.
Yes,
so this is sort of high level high school.
Oh, very high level, yes.
Very high level high school level mathematics problems. What do you think about the system, and maybe what is the gap between this system that is able to prove the high school level problems versus graduate level problems?
Yeah, the difficulty increases exponentially with the number of steps involved in the proof. It's a combinatorial explosion. Right? So the thing of large language models is that they make mistakes. And so if a proof has got 20 steps and your large language model has a 10% failure rate at each step of going in the wrong direction, it's just extremely unlikely to actually reach the end.
Actually, just to take a small tangent here, how hard is the problem of mapping from natural language to the formal program?
Oh yeah, it's extremely hard actually. Natural language, it's very fault tolerant. Like you can make a few minor grammatical errors, and a speaker in the second language can get some idea of what you're saying. But formal language, if you get one little thing wrong, I think that the whole thing is nonsense.
Got it.
Even formal to formal is very hard. There are different incompatible proof assistant languages. There's Lean, but also Koch and Isabelle and so forth. Actually, even converting from a formal language to formal language is an basically unsolved problem.
That is fascinating. Okay, so but once you have an informal language, they're using their RL trained model, so something akin to AlphaZero that they use to Go, to then try to come up with proofs. They also have a model, I believe it's a separate model for geometric problems. So what impresses you about this system, and what do you think is the gap?
Yeah, we talked earlier about things that are amazing over time become kind of normalized. So yeah, now somehow it's of course geometry is a solvable problem.
Right, that's true. I mean, it's still beautiful.
These are great works. It shows what's possible. I mean, the approach doesn't scale currently. 3 days of Google's server time to solve one high school math problem. This is not a scalable prospect, especially with the exponential increase in as the complexity increases.
We should mention that they got a silver medal performance.
The equivalent of, I mean, yeah,
Equivalent of a
yeah, I
silver
mean,
medal performance.
so first of all, they took way more time than was allotted, and they had this assistance where the humans helped by formalizing. But yeah, also they're giving themselves full marks for the solution, which I guess is formally verified. So I guess that's fair. Yeah. There are efforts. There will be a proposal at some point to actually have an AI math Olympiad where, at the same time as the human contestants get the actual Olympiad problems, AIs will also be given the same problems with the same time period, and the outputs will have to be graded by the same judges, and which means that it will have to be written in natural language rather than formal language.
Oh, I hope that happens. I hope that this IMO happens. I hope next one.
It won't happen this IMO. The performance is not good enough in the time period, but there are smaller competitions. There are competitions where the answer is a number rather than a long form proof, and that's AIs are actually a lot better at problems where there's a specific numerical answer, because it's easy to reinforcement learning on it. Yeah, you got the right answer, you got the wrong answer. It's a very clear signal. But a long form proof either has to be formal, and then the lean can give it thumbs up, thumbs down, or it's informal. But then you need a human to grade it to tell. And if you're trying to do billions of reinforcement learning, runs, you can't hire enough humans to grade those. I mean, it's already hard enough for the large language models to do reinforcement learning on just the regular text that people get. But now if you actually hire people and not just give thumbs up, thumbs down, but actually check the output mathematically, that's too expensive.
So if we just explore this possible future, what is the thing that humans do that's most special in mathematics? So that you could see AI not cracking for a while. So inventing new theories, so coming up with new conjectures versus proving the conjectures, building new abstractions, new representations, maybe an AI Terence Tao with seeing new connections between disparate fields.
It's a good question. I think the nature of what mathematicians do over time has changed a lot. So 1,000 years ago, mathematicians had to compute the date of Easter, and there's really complicated calculations. But it's all automated, been automated for centuries. We don't need that anymore. They used to do spherical trigonometry to navigate how to get from the old world to the new, or something. Very complicated calculations, again, been automated. Even a lot of undergraduate mathematics, even before AI, like Wolfram Alpha, for example, it's not a language model, but it can solve a lot of undergraduate level math tasks. So on the computational side, verifying routine things like having a problem and say, here's a problem in partial differential equations. Could you solve it using any of the 20 standard techniques? They have, yes, I've tried all 20, and here are the 100 different permutations, and here's my results. And that type of thing, I think it will work very well. Type of scaling to, once you solve one problem, to make the AI attack 100 adjacent problems. The things that humans do still, so where the AI really struggles right now is knowing when it's made a wrong turn. And it can say, oh, I'm going to solve this problem. I'm going to split up this problem into these two cases. I'm going to try this technique. And sometimes if you're lucky and it's a simple problem, it's the right technique and you solve the problem. And sometimes it will have a problem. It would propose an approach which is just complete nonsense. But like it looks like a proof. So this is one annoying thing about LLM generated mathematics. So we've had human generated mathematics that's very low quality. Submissions people who don't have the formal training and so forth. But if a human proof is bad, you can tell it's bad pretty quickly. It makes really basic mistakes. But the AI generated proofs, they can look superficially flawless. And it's partly because that's what the reinforcement learning has actually trained them to do, to make things, to produce text that looks like what is correct, which for many applications is good enough. So the errors are often really subtle, and then when you spot them, they're really stupid. Like no human would have actually made that mistake.
Yeah, it's actually really frustrating in the programming context because I program a lot, and yeah, when a human makes low quality code, there's something called code smell, right? You can
Yes.
tell, you
Yeah,
can tell
yeah.
immediately, like
Right,
okay, there's
yeah.
signs. But with AI generate code,
They're odorless.
and then you're right.
Yeah.
Eventually, you find an obvious dumb thing that just looks like good code.
Yeah. So
it's very tricky and frustrating for some reason to
so
have to work.
So the sense of smell. Okay, there you go. This is one thing that humans have, and there's a metaphorical mathematical smell that it's not clear how to get the AIs to duplicate that. Eventually, I mean, so the way AlphaZero and so forth to make progress on Go and chess and so forth is in some sense they have developed a sense of smell for Go and chess positions. That this position is good for white, it's good for black. They can't enunciate why, but just having that sense of smell lets them strategize. So if AIs gain that ability to sort of a sense of viability of certain proof strategies, so you can say, I'm going to try to break up this problem into two smaller subtasks, and they can say, oh, this looks good. The two tasks look like they're simpler tasks than your main task, and they still got a good chance of being true. So this is good to try. Or no, you made the problem worse because each of the two subproblems is actually harder than your original problem, which is actually what normally happens if you try a random thing to try. It's very easy to transform a problem into an even harder problem. Very rarely do you transform to a simpler problem. So if they can pick up a sense of smell, then they could maybe start competing with human level mathematicians.
So this is a hard question, but not competing, but collaborating.
Yeah.
Hypothetical. If I gave you an oracle